Everybody, welcome back. This is our lecture for Chapter 7 in the textbook. And Chapter 7's lecture is all about electron configuration and periodic table, but really it's about, you would consider Chapter 7 to be about everything we notice happening with atoms and why. So we try to use electron configuration and to kind of explain why atoms do a couple things. Let me give you a couple examples. Okay, so we have a tool in science called photoelectron spectroscopy, or PES for short. And we talked about this a little bit. It's based off the photoelectric effect. Okay, so let me pause it right there. So the photoelectric effect we talked about in chapter 6, and basically you take some kind of light source, all right, and what we were able to do with this light source, whether you want to call this a light gun or whatever, is we were able to change the wavelength. And we were able to go from very long wavelength, which is low energy, and we tune it, essentially turn the thing all the way up and go to very small wavelength or very high energy. And what we find with the photoelectric effect is the idea that shining light on an atom will actually cause an electron from the atom to get ejected. All right, so if I imagine I have an atom here, and this atom has a whole bunch of electrons. Let me pause and draw some electrons in this atom. So let's say this is atom magnesium, and magnesium has 12 electrons with 2 valence electrons. If we start with the longest wavelength or the lowest energy, and we start shining this light onto our metal sample. So imagine I have a sample of magnesium metal, and I put inside my photoelectron spectrometer, and I start turning up the wick, so to speak. I start turning up the energy, and eventually the light reaches enough intensity to start pulling off electrons. So the first electron to come off will be this one. And we know that based on our theory of atoms, that valence electrons, the electrons out here, are basically held the weakest to the nucleus. You know, one thing to think about is the nucleus is this gigantic ball of positive charge, and electrons are all negative. Well, if this is a magnesium nucleus, the magnesium is going to have 12 protons, or a plus 12 charge here in the nucleus. And there's 12 electrons, so there's got to be a negative 12. But one of the things we forget is that positive charges attract negative charges. So if this represents the electron that's right here, and this represents the nucleus, physics tells us that the positive charge and the negative charge will be attracting each other. So much so that there is actually a really strong force which is causing these two things to be attracted to each other. Okay, that's fine. If I had one proton and one electron, I think everybody agrees it's the end of the story. We get the idea. This electron is very strongly attracted to the proton, and that's why the electron doesn't fly away in the first place. But what if we have this atom that has, if you notice, this electron is way out here, and the protons are way in here, and in between, let me just highlight this proton a little bit differently. Sorry, highlight the electron. This electron right here, the one which we're going to kick out by shining light on it, it's not alone. It kind of has a lot of other electrons in the way. So what this is like is, here's my electron, and it's all the way on the outside of the atom. And my nucleus is way over here. It's a big plus 12 charge because of the 12 protons. Well, this negative electron has 11 other, well, realistically, because this electron is kind of not blocking it, let's call it 10 other electrons that are in the way. And these are all negative charge. So what happens to this electron? Does this electron out here, does this valence electron way out here, does it feel the full force of this positive 12 nucleus? Right? Just kind of think about that for a second. Does this electron all the way out here feel the full force of this nucleus if there's a whole bunch of negative electrons in the way? And the short answer is no. And based on this, these electrons that are kind of in the way blocking, or the word that chemists use is shielding. These electrons that are shielding this outside electron cause this electron, well, it causes this electron not to be held as tightly to the nucleus, right? The term we're looking for here is something called binding energy. And that's the term chemists use to describe how much force or how much energy is this electron actually being attracted to the nucleus. If it's one proton and one electron, this force of attraction is huge. But the fact that there is 10 electrons in the way of this one causes this force of attraction to be, well, it's kind of tiny or very small. So the binding energy, the amount of energy holding this electron onto the nucleus of the atom, is very small, right? So we can actually measure this binding energy using this process of photoelectron spectroscopy. All we do is we take our light source, we turn up the energy, and there's a dial which has number readouts on it which tell us how much energy the light is actually shining onto the sample right now. And what we do from this experiment is this. We essentially create a graph. And the graph is number of electrons versus binding energy. So let's do this. Let's put low binding energy over here and high binding energy over here. And what we find out is the first electron to get peeled away here has relatively low binding energy because of the reasons we just discussed. It's really far away from the nucleus, and it's got a whole lot of other electrons blocking it. So eventually, we build up a graph that looks like this. We find out that there's 2 electrons. We pull off the first electron, then we pull off the second. And as we go further, the electrons closer and closer to the nucleus, have a huge, take off way more energy. It costs us way more energy to remove electrons closer to the nucleus than it does farther away. So this is a phenomena that scientists had to explain using a little bit of knowledge about the atom and positive and negative charges. So this is one reason for kind of the lecture we're putting at you right now. How do we explain what atoms are actually doing now that we know a whole bunch of things about them? Now that we know about their charges, now that we know about their electron configurations, how can we use that to explain things? So photoelectron spectroscopy is a technique that allows us to study exactly where electrons are in an atom. Okay, so I'll give you another example of how atoms behave and why we need to kind of study them. The next process we're talking about is called electronegativity. Now, this is a phenomena that we're going to talk about tonight, but we can kind of describe the effect of this phenomena. If you look at the structure for a water molecule, water is an interesting molecule because it's bent. Its three-dimensional structure is actually bent. And we haven't really talked about why yet, but maybe we'll kind of put a little bit in here right now. And I apologize for my terrible drawing, but water is actually bent. Water forms 2 covalent bonds with a hydrogen to an oxygen and then a hydrogen to another oxygen. And it does this, if you think about this in terms of the electron configuration of all these atoms, oxygen has an electron configuration of 1s2, 2s2, 2p4. If you look at the orbital notation for oxygen, we get 1s, 2s, and then 2p. Remember, the 2p splits into 3 different equal energy groups, which we ended up calling the 2px, 2py, and the 2pz. So with orbital notation, we have spin up, spin down electrons, spin up, spin down, spin up, spin up, spin up, and then a spin down. So one way to look at this is oxygen. If you remember our ideas talking about what makes atoms stable, most atoms want to have 8 valence electrons in order to become stable. Where are they going to go? Oxygen needs to get 2 more valence electrons to make our valence shell. Remember, the valence shell is always the outermost s and p orbitals to make our valence shell have 8. Right now our valence shell has 2 plus 4 is 6. If you look at the orbital notation, oxygen is missing 2 electrons right here. So if oxygen can share electrons with 2 other atoms, it can get a stable electron configuration with 8 valence electrons. So come along 2 hydrogens. A hydrogen has electron configuration of 1s1, or an orbital notation of 1s with a spin up arrow. So what happens is here, what we do when we draw diagrams of bonds, this stick actually represents a pair of electrons being shared. So let me erase the stick here real quick, or the bond. Each bond represents a pair of electrons that's being shared. And so we're getting a little ahead into bonding right now, but that's okay. So hydrogen has an electron of its own. Hydrogen has a 1s electron. In fact, each hydrogen has a 1s electron. But oxygen has these 2p electrons. Oxygen has a 2p electron over here that it can share with this hydrogen. Oxygen has a 2p electron here, which it can share with this hydrogen. So what scientists do to represent the fact that these atoms are going to share electrons is they draw a line in between. So instead of drawing the dots, they draw a line, and each line represents a bond. So oxygen can share its blue electron with hydrogen, and we end up with this. Hydrogen ends up getting a second electron, and it fills its 1s. Hydrogen's electron configuration turns into 1s2. The oxygen does the opposite. The oxygen takes an electron. Take is too strong of a word. The oxygen is being shared, these 2 electrons from each hydrogen, and the other electrons come in here and fill these spots as spin downs, or this electron configuration changes from 2s2 2p4 to 2p6, and now there's 8 valence electrons here, and we can see there's 8, 1, 2, 3, 4, 5, 6, 7, 8 valence electrons here. So the process of forming this covalent bond, the process of forming the covalent bond here gives hydrogen and oxygen this particular shape. But there's a little bit more, because oxygen has valence electrons that are already paired. The 2s and this part of the 2p are electrons in oxygen in its valence shell that are already paired. So technically oxygen has what we call a lone pair of electrons here and a lone pair of electrons here. And as we're going to find out when we talk about bonding, the fact that water as a molecule has 1, 2, 3, 4 places around it forces water to have this what's known as tetrahedral shape. And as a result of tetrahedral, tetrahedral shape, the angle between hydrogen, oxygen, and hydrogen, this angle is going to be 109.5 degrees. So in other words, water is going to be a bent molecule. Okay, so wow, we went over a lot of stuff there, and don't worry, we're going to cover this again when we talk about bonding, but the idea is electronegativity is a phenomenon we haven't even talked about yet. It turns out we observe this. So what I'm showing you here is 2 electrons kind of being shared equally between the hydrogen and the oxygen. But when we examine the water molecule, that's not actually what happens. If I redraw my molecule, the molecule, it turns out oxygen still has its electrons here and here that it's sharing with the hydrogen, but oxygen has the ability, it turns out oxygen has the ability to pull these red electrons from the hydrogens closer towards the oxygen. So instead of these red electrons being near the hydrogens, they're actually a lot closer to the hydrogens. So that phenomena does this. Hydrogen only has 1 electron to begin with, right? So if its electron is being pulled away from it, it has the effect of making hydrogen a little tiny bit positive. This is the lowercase Greek delta. This hydrogen's electron has been pulled away from it. It makes this hydrogen a little bit positive. And oxygen has electrons pulled closer to it, so it makes the oxygen a little tiny bit negative. So this is another phenomena that we observe occurring, and the phenomena is known as electronegativity, because some atoms have a greater ability to pull electrons toward it. So this is another phenomenon we observe about atoms, and we need to be able to explain it. All right, so let's start our talk for tonight. So this is kind of a list of all the things we're going to talk about in Chapter 7. Some, I'm not going to lie to you, some more than others. We've already talked quite a bit about the development of the periodic table. We've talked about periodic trends. In fact, we spent a lot of time talking about Mendeleev and the arrangement of periodic table in terms of reactivity, atomic radius, etc. And I'm going to, because we've talked about it before, I'm not going to put a lot of information on that tonight. So tonight we're going to focus on the chapters that are kind of in the middle. Modern periodic table, effective nuclear charge. And this is probably one of the most important trends we're going to notice on the periodic table tonight. I shouldn't say effective nuclear charge is a trend, although it does have one, but it's used as to be able to explain all the other properties that we observed. And there are a host of properties that can be explained by effective nuclear charge. The radius of an atom can be explained by effective nuclear charge. Something called the ionization energy, which I'm going to abbreviate terribly. Electronegativity, which we talked about before. There's a host of properties, periodic properties or periodic trends that can be explained by this one phenomenon known as effective nuclear charge. We're going to talk a little bit about electron configuration of ions, and then we'll kind of wrap this up. We're definitely going to have two lectures for this particular, two video lectures for this particular segment. There it is. All right, ready? Here we go. So we have to talk about Mendeleev a little bit. We know that Mendeleev was the first person to really develop set us on the right path with a modern periodic table. He took atoms that he knew of at the time, arranged them in order by their mass, and you see familiar patterns. Yet the way he arranged them, we started to see atoms that were in kind of the same rows had very, very similar properties. And the rest is kind of history. We kind of remember everything we talked about from that. And the rest is the development of the modern periodic table. So the modern periodic table it's arranged by, I guess we can call this a couple different ways. It's arranged by atomic number, mostly. So we go from, atomic number, by the way, is protons. So we go from least number of protons across the table to most, and we keep jumping back down. But there's more. I mean, we see lots of trends in the periodic table. Here's the periodic table, by the way. So the numbers that go along with each atom, hydrogen is 1, and helium 2, and lithium 3, and so on, are number of protons. So the modern periodic table is definitely arranged by number of protons. Number of protons is king. But if you remember our lecture from last week, we also know that this periodic table is arranged by which orbital, whoops, that line is terrible. It's also arranged by the orbital that is being filled. Orbital. Okay, so any atom that is in groups 1 and groups 2, the very last electron that's being filled in these atoms is being filled in an s orbital. Sodium and magnesium, their very last electrons, out of the 12 electrons for magnesium, the last 2 of them are going to go into a 3s orbital. The last electron for cobalt is going to go to a 3d orbital. The last electron for oxygen goes into a 2p, and so on. Even for elements down here, we know these elements are filling, the last electrons to be filled in these go into f orbitals. So the periodic table is also broken up into what type of orbital is being filled where. S's, D's, P's, and F's. So it's kind of a modern sense of periodic table, but the one thing we stressed, and this was like, we did this periodic table activity a couple weeks into the course, we stressed valence electrons. And this was the essential trend that we came up with that night that we worked on the periodic table card activity. That if you're in the same group, you have the same number of valence electrons. So the first things first, there's a set of elements in the periodic table we know as the main group elements. And main group elements are, there's usually like a Roman numeral numbering style. They are everything except the transition metals. 1, 2, 3, 4, 5, 6, 7, and then 8. And with the exception of helium, Helium only has 2 valence electrons. The group that you're in, the main group that you're in, that tells you the number of valence electrons that you have. So every atom in group 1 has 1 valence electron, and every atom in group, let's say 3, has 3 valence electrons, and so on. All right. Okay, so main group elements are everything it's group 1, 3, 4, 5, and 6. All the transition metals and the lanthanides and actinides down here are not considered main group elements. And but even if you are like an element here in copper, copper is going to have the same number of valence electrons as silver and gold and whatever the next atom is down there that I can't read because the page is too small. Okay, so valence electrons, valence electrons, valence electrons is the important trend. So every atom that's going to be in group 1 is going to have an S1 configuration, group 2 is S2, group 3 is going to be S2P1, group 4 is S2P2, and so on. And on that note of valence electrons, we have to talk about which electrons are valence electrons. It's always the outer s and p orbitals. I'm not saying whatever s and p's are the last ones in the configuration is it. For example, an atom like magnesium. Magnesium has an electron configuration of 1s2, 2s2, 2p6, 3s2. The outermost s and p are the valence electrons. I don't mean take this s and this p. Valence electrons always have to have the same period number that goes along with it. Remember, the number that comes in front of all of these, the number that comes in front is what's known as n. It is the principal quantum number. Okay? So valence electrons have to have the same principal quantum number. So magnesium only has 2 valence electrons, but an atom like chlorine over here, chlorine's configuration is 1s2, 2s2, 2p6, 3s2, 3p5. So the valence electrons for chlorine are going to be in the 3, the third principal quantum number. So no surprise, chlorine is in group 7. It's going to have 1, 2, 3, 4, 5, 6, 7 valence electrons. Okay? So d orbitals, f orbitals are never valence electrons. It's always the outermost s and p. All right? So an atom like right here, this particular atom, vanadium, does not have 5 valence electrons. It is going to have it has 4s2, 3d3. It's going to have 2 valence electrons, okay, because of the s. The 4s2 is going to give it 2 valence electrons, okay? So on the periodic table, we have 3 main types of elements. We have metals, nonmetals, and metalloids. And metals have, we talked about properties of metals before. They are shiny. They have what's called luster. They are malleable. They can conduct electricity plus heat very well. And typically with metals, because these things form amazing crystal structures over and over and over with millions and millions of atoms, we end up using empirical formulas. But in addition to metals, we've got nonmetals. Nonmetals are typically exist as polyatomic or diatomic molecules, and there's not many nonmetals in the periodic table. Hydrogen, carbon, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. There's a couple cases like phosphorus can form P4 and sulfur can form C8, but carbon, which is one of our nonmetals, is just carbon. All right. Nonmetals they're typically brittle. They're the exact opposite behavior of metals, and then we end up with noble gases and metalloids. Noble gases are non-metals, but these are things that have full valence shells, so they rarely react to form compounds. Metalloids form three-dimensional network structures like metals do, and they typically have properties in between metals and nonmetals. But we're not worried too much about this tonight. Okay, so let's get to this. Effective nuclear charge. How do we use this? What is it? What is it good for, etc. So as we were saying earlier, effective nuclear charge can explain a lot of things that we observe about the atom, like what's the radius of an atom? Why does an atom have a radius it does? What happens when an atom gives up or takes an electron? What happens to its radius? Ionization energy. We talked about this before with photoelectron spectroscopy. How much energy does it cost to remove an electron? Electron affinity is some nonmetals really want to have electrons towards themselves. Electronegativity is a related property. It has the ability of an atom to draw bonded electrons towards it, like the example we had with water, and even metallic character. So let's talk about it. Effective nuclear charge is one of those things where it's a topic you kind of have to chew on for a while to kind of really understand what it is, and we're going to talk a lot about it. So effective nuclear charge is literally, it's a combination of two terms. So if we remember, nuclear charge or atomic number is literally the number of protons in the nucleus of an atom. An atom that has one proton will have a nuclear charge of +1. An atom that has 17 protons will have a total nuclear charge. When you add up all the protons, we'll have a charge of +17. And if you remember, we talked about this before. We talked about this when we were writing formulas for ionic compounds. We talked about what happens if you have 17 protons and 17 electrons. You have a total positive charge of +17 and a total negative charge of -17. If you remember going back, we talked about that before. But um, what did I just do? So as we said before in the very first example, if you have an atom that has lots of electrons, a many electron atom, the electrons on the outside are partially shielded from experiencing the full positive charge of the nucleus. And the example we gave is you've got this one electron all the way on the outside. I think we used the example of magnesium. And there's 10 other electrons in the way of the nucleus that has a +12 charge. So this electron all the way on the outside is kind of, it's blocked. And I hate to use a football reference, but there's a play in football. Actually, it's not just football. There's plays everywhere, which is known. You shield the other person. I'm trying to think of the sport where, hockey. Hockey has a shield set up. The goalie can be shielded from actually seeing where the puck is. You don't want to shield the goalie with your own player because then the goalie can't tell what's going on. So it's a similar analogy, okay? These electrons that are in the way are maybe blocking is a good word, or the other word that's used is shielding. So this electron on the outside does not feel the full brunt of this +12 charge. Imagine this is like the sun, okay? This is the sun, and this is you. You are a person on the earth that wants to feel the warmth of the sun, like every other person in the northeast of the United States on April 1st is not feeling the full effect of the sun. So how do you prevent this person over here from feeling the full effect of the sun? You put a whole bunch of clouds in the way. And the clouds shield the person from the full effect of the sun. Everyone knows what it feels like to stand outside on a hot summer's day, and you stand out in the sun, you just feel like you're being cooked, you're being baked by the sun. Well, throw a whole bunch of clouds in the way, and you hardly feel that the sun is out at all. The sun is, I heard a good one, the sun is socially distancing today. Anyways, so this is what happens to this electron on here. It's shielded by these electrons. So enter the concept of effective nuclear charge. Effective nuclear charge is the positive charge that this electron out here actually feels. So in the example we gave in the first few minutes of the lecture, we said in a one electron atom, the one electron feels the full force of the nucleus. If you imagine taking this same example put this negative electron out here and put a plus 12 nucleus, if there's nothing in the way, this electron feels the full force of the nucleus and is actually attracted more to the nucleus because it feels the full force of it. But because I'm putting a whole bunch of stuff in the way, a whole bunch of negative charges, this electron is shielded or blocked and it doesn't feel the actual charge. Okay? So what is effective nuclear charge and how do we calculate it? So effective nuclear charge is defined as this. It is defined as the total positive charge of the nucleus. And this is super easy to find. You just look at whatever the atomic number is. So if I have an atomic number of 17, the total positive charge of the nucleus is going to be plus 17. Okay? So take the atomic number and just put a positive sign in front of it. Minus, this is the tricky part, minus the number of core electrons. Now, core electrons are a little bit trickier to find. Let's talk about how to find number of core electrons. So imagine this atom that has a plus 17 charge. It is going to also have 17 electrons initially. So let's draw some electrons in. First shell can hold 2 electrons, and then the second shell can hold 8. So let me speed this up. Okay, so first shell can hold 2 electrons, second shell can hold 8, third shell has 7 in it. So obviously this atom is missing an electron right here. So we know that this atom is going to be in group 7 of the periodic table. Okay, what is a core electron? Well, if I'm trying to find the effective nuclear charge, let's say I want to find the effective nuclear charge of these electrons here. Let's say the valence electrons. And usually when people talk about effective nuclear charge, they're trying to talk about effective nuclear charge on valence electrons. So what effective nuclear charge is a valence electron in an atom going to experience? We take the total positive charge, in this case it's plus 17, minus the number of core electrons. And here's the thing, core electron is any electron closer to the nucleus than a valence electron, okay? So where are all the valence electrons? They're here, 1, 2, 3, 4, 5, 6, 7. These are not core electrons, right? And this is where it gets a little bit confusing. Valence electrons are not core electrons. What are core electrons? Any electrons that are closer to the nucleus than the core, which means every single one of these electrons here that I draw inside my really sloppily drawn circle becomes a core electron. How many electrons are inside that circle? There's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this atom is going to have 10, there we go, 10 core electrons. So valence electrons are not core, okay? Keep that in mind. You could probably use that as the name of a band. So for this particular problem, we've got total positive charge is plus 17, minus the number of core electrons is 10. So the effective nuclear charge of any one of these valence electrons on the outside, any one of these 7 valence electrons will have an effective nuclear charge of only 17 minus 10 or plus 7. Okay, so just kind of think about this for a minute. An electron on the outside of the atom is being blocked by all the electrons that are in the way, and it doesn't feel the full force of the sun of the nucleus. So these are electrons that are blocking it. Instead of this electron on the outside feeling an effective nuclear charge of plus 17, that's a terrible 17. So instead of this electron right here feeling an effective nuclear charge of plus 17, the full brunt of the nucleus, pulling it and attracting it towards it, it only feels an effective nuclear charge of plus 7. What are some consequences of this? Well, for one, it is a whole lot easier to remove a valence electron in an atom because this valence electron is not being attracted to the atom as strongly as core electrons are. That's really what this is saying. Valence electrons have a lower effective nuclear charge. Therefore, they are easier to remove from the atom. Let me write that down. So valence electrons are easier to remove from an atom because the effective nuclear charge is lower. So what that means is core electrons are require more energy to remove than valence electrons. So core electrons require more energy to remove because core electrons experience a higher effective nuclear charge. Let's look at this example again from the standpoint of the core electrons. Okay, so let's take the same atom, and we know this atom has a plus 17 charge in the nucleus. But now let's imagine we're looking at it from the perspective of the electrons in the second shell. So remember, there are 2 electrons in the first shell, and 1, 2, I'm going to speed this up so I don't make you sit here. Okay, so I drew in the 8 second shell electrons. I'm not going to draw in the third electron. So this is a hypothetical. What would the effective nuclear charge? Let's make one of these electrons super special, and let's use purple. Let's say this electron right here. I want to know what effective nuclear charge that particular electron is going to experience. Why is it that core electrons require more energy? Well, the short answer has got to be this. Because the effective nuclear charge must be larger. So the only reason why it would be more difficult to remove this electron than an electron from the outside is because this electron must have a higher effective nuclear charge. Let's find out. Okay, so effective nuclear charge is equal to number of protons plus 17. I keep drawing the 7 first. Plus 17 minus the number of core electrons. Aha, I tricked you. Well, if this is the electron that we're concerned with, then all of the electrons that are in this shell can't be core electrons. Instead, where are the core? They are here. These 2 electrons are now the core electrons. All right, if we're talking about the effective nuclear charge that this electron is experiencing. So now the effective nuclear charge is 17 minus 2, which is huge. So the electrons that are in the second shell experience an effective nuclear charge of plus 15. Remember, the electrons that are out here experience an effective nuclear charge of, what did we say it was? Plus 7. So valence electron has an effective nuclear charge of plus 7. This second shell electron has an effective nuclear charge of plus 15. So it's almost experiencing the full force of the nucleus, right? So it's very difficult to remove. When atoms are going to have their electrons removed, usually it's going to be the valence electrons. So hopefully this has made sense, right? This concept of effective nuclear charge and how to find it. I'm going to give you one more analogy, all right? So here's a hypothetical. Imagine you were going to a rock concert. So here's your stage, and along the stage you've got the people sitting out here in the seats, and the people in these seats have the best seats. But let's say we're talking about going to see the rock concert by the aluminum atom, and aluminum is an atom that has 13 protons and 13 electrons. So we know this, if this is the nucleus, it's got to have a plus 13 charge. Well, there's only going to be 2 electrons in this seat. And then we go back a little bit farther, and there's another set of seats. And there's going to be 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8 electrons in these seats. And we go back even further, or farther. And in this row, there's going to be 1, 2, 3 electrons, and there it is. So if we want to think about this, if you're all the way back out here, you're being shielded. You're being blocked by the full force of this positive charge. These 3 electrons are being shielded by how many? How many electrons are these electrons being shielded by? Count them. They're being shielded by everything in front of them, which means 8 plus 2, and they're being shielded by 10 electrons. So the electrons out here are going to have an effective nuclear charge of plus 13 minus the 10 electrons that are blocking them, or an effective nuclear charge of plus 3. Okay, let's go to the second row here. So imagine we're talking just about these electrons right now and not the electrons on the outside here. So how many electrons are, I mean, they're not quite the first row, they're not the best seats, but they're still being blocked. How many electrons, how many electrons are in front of these 8? How many electrons are these being shielded by? Well, the only people in front of these 8 are these 2, so they're only being shielded by 2 electrons. So the electrons in this second row back are going to have an effective nuclear charge of 17, sorry, I don't know where I got 17 from, plus 13 minus the 2 electrons in front of them, they're going to have an effective nuclear charge of plus 11. So they're going to feel a lot more attraction. These electrons are going to be a lot more attracted to the nucleus than these are. So maybe I can draw little arrows here, and the arrows represent the magnitude of the attraction that these electrons are going to feel to the nucleus. And then we get up to the first row. Now the first row, are the first row electrons being shielded by anything? Is there anything in front of them? And the answer is no. There's nothing blocking these 2 electrons from the nucleus. So the electrons in this row are going to have an effective nuclear charge of plus 13 minus, well, what's in front of them? Nothing. 13 minus 0. They are going to have an effective nuclear charge of plus 13. So these electrons are seeing the sun or the nucleus at all times of the day. There's nothing in the middle blocking these electrons from the sun. As a result, they are going to feel the largest attraction to the nucleus. So huge attraction, attraction, teeny tiny attraction. So which of these 3 sets of electrons do you think are going to be the hardest to remove from the nucleus? Wait for it, wait for it. Yeah, it's going to be these. If we're trying to remove electrons, these are going to be the absolute hardest electrons to remove from this nucleus. These 3 are going to be the easiest. This is why we always say, by the way, these electrons out here are our valence electrons. They only experience a plus 3 charge from the nucleus. They're not really that strongly attracted to the nucleus, and that's why aluminum can so easily do what? It can react. Aluminum can react. The effective nuclear charge is really small on these electrons. This atom can just lose electrons at will almost. Take a piece of aluminum metal and go put it in your backyard. It's going to come back, it's going to react pretty easily. Okay? Okay, so effective nuclear charge, really, really important. Now, there's a couple things that happen repeatedly with effective nuclear charge if we go to the periodic table. So these atoms here, the atoms here are effectively have no 0 core electrons. I don't know why I wrote E for that. So the atoms, let's get rid of purple. We're done with purple, right? The atoms in the first period, this is period 1 on the periodic table, have 0 core electrons. Once we go out, the atoms that go all the way across here in period 2 are going to have 2 core electrons. The atoms in period 3 have all of the electrons that came before it in their way. So period 3 are going to have 8 plus 2 core electrons. They're going to have 10 core electrons. Period 4 is going to have 18 core electrons. Period 5 is going to have, hold on, I have to do that math in my head. Oh, I figured it out, 36. So the number of core electrons is going to increase as we go down a period. But the thing is, every atom going across this period is going to have 10 core electrons. The number of core electrons does not change going across a period. However, the effective nuclear charge does. All right, so let's talk about this. Let's talk about this for a second. Let me put a simpler periodic table up here to look at. Okay, let's take a small section of the periodic table. So we know if we're kind of looking at core electrons and plotting them going down, the first period going across has 0 electrons, 0 core electrons. The second period has 2 core electrons. The third period has 10. The fourth period has 18 core electrons, right? So, and our effective nuclear charge equation is this. Effective nuclear charge is, how do I say this? Total positive charge minus core electrons. Okay, so let's do this. let's start with lithium right here. Lithium has a total positive charge of 3, right? So for lithium, it has total positive charge, and we're going to find let me rewrite this. We're going to find the effective nuclear charge for lithium and go across the periodic table, okay? So effective nuclear charge for lithium is going to be total positive charge of 3 because it has 3 protons, minus the fact that lithium right here is going to have 2 core electrons. So lithium is going to have an effective nuclear charge of +1. So again, we're talking about the effective nuclear charge on the 1 valence electron for lithium, okay? So again, the effective nuclear charge we're talking about is only for, this is only for valence electrons on the atom. Obviously, lithium has 3 electrons. We're not talking about the effective nuclear charge on all the electrons. All right, go over to the next atom. The next atom is boron. All right, boron has a total positive charge of 4. There's 4 protons, but how many core electrons does it have? It has 2. So 4 minus 2, it's going to give us an effective nuclear charge of +2. So both of boron's 2 valence electrons are going to have an effective nuclear charge of +2. All right, next atom over is um, I just said, I totally just said wrong. This isn't boron, it's beryllium. Beryllium right here will have an effective nuclear charge. Next atom over is boron. So we're talking about boron now. Effective nuclear charge. Boron has 5 protons, so it's going to be 5. Still, it's still in the second period, so it still has 2 core electrons. Minus 2 is +3. Do we see a pattern going on? Yeah. +1, +2, +3. If we keep going across, +4, +5, +6, +7, and then +8. Just so we're on page, let me just do this one right here. This atom right here is fluorine. Just so the pattern is not a fluke. So for fluorine, fluorine has 9 protons. So 9 minus the fact that it still has 2 core electrons, 9 minus 2 equals +7. Okay, now obviously hydrogen and helium are a little bit different. Hydrogen doesn't have any core electrons, it only has 1 proton, so it's going to have an effective nuclear charge of +1, and helium has no core electrons and 2 protons, so it's going to be +2. So helium is kind of an oddball right now, but let's go on to this atom. Atom in this spot is sodium. Okay, let me pause and erase. Okay, so this atom right here is sodium, and the number of core electrons has changed now. Now sodium is going to have 10 core electrons. So sodium has 11 protons, so a total positive charge of 11 minus 10 core electrons. So even though sodium is a bigger atom, even though sodium has more electrons total, it still is only going to have an effective nuclear charge of +1. Well, just kind of take a minute and look at this. I got +1, +1, +1 all in the same group. Maybe if I do the next atom over here, magnesium, I'll get a +2. So let's check. Magnesium, effective nuclear charge. Magnesium has 12 protons, or a positive 12 charge, minus 10 core electrons. Yep, we got it, +2. So the trend in effective nuclear charge is that the effective nuclear charge for a group is going to be the same across the periodic table. If you're in group 3, you'll have an effective nuclear charge of +3, +4, +5, +6, +7, +8. So that continues going down. So the trend we see in the periodic table is effective nuclear charge increases going across the periodic table, but going down on the periodic table, it stays the same. Okay? Effective nuclear charge, I totally wrote this. I wrote this trend wrong, I'm sorry. The effective nuclear charge stays the same going down a group. Okay? Okay, look, it's 49 minutes in. I have to pause and stop this one so I can make lecture 2. I hope you're hanging with me, okay? All right, good.